Welcome to qnawire.
Hi, so for this problem we're asked to find the concentration of different ions into reactions where we have an almost insoluble solid. So the first one we have aluminum hydroxide. So this solid it is going to turn into one equivalent of the aluminum 3 plus ion plus 3 equivalents of the OH minus ion, and we're given the value for the solubility product constant. Let's remember that the definition of KSP is equal to the product of the concentrations of aluminum times the concentrations of OH minus elevated to the stoichiometric coefficient, in this case that is 3. Okay? So most of the professors in this type of problems, one section of the grading of the marks is going to be the ice table. So at the beginning we have a pure solid, so we don't take that into account, and we have 0 of each of the ions. Next up, the change is that an X portion of the solid is going to be appearing on solution. So that means that plus X and plus 3X, it is going to go into the change of the ions. So at the equilibrium, we are still going to have the solid minus that X portion, but that doesn't matter because pure solids do not take part of the equilibrium constant. And at the equilibrium, we have the quantities X and 3X. Okay? So now replacing these two values, the X and the 3X, in the KSP constant, we have X times 3X cubed. And this is going to be simply 27x to the 4. 3 cubed is 27, x cubed times x is x to the 4. So now we can take our value for KSP and solve for x. This is 27x to the 4. This is 3 times 10 to the minus 33. This means that x, it is going to be 3 times 10 to the minus 33 divided by 27, and all of this elevated to the 1/4. And our result for x is, rounding up to 2 decimal points, it is going to be 3.25 times 10 to the minus 9 molar. So now we know the value for x, so we can know the value for our concentrations. For aluminum 3 plus, the value of the concentration is equal to x, so simply 3.25 times 10 to the minus 9. And for the case of OH minus, the concentration is 3 times x, as we can see from here and from here. So we simply multiply that value for 3. Since we rounded things up, this is going to be 9.75 times 10 to the minus 9. And both of them are in molar. In this case, depending on your professor, you may want to provide more decimal values. Here I'm just taking the standard of just taking 2 decimal points, which is common in most of the chemistry courses. But you can actually take this value and verify that the result is going to give you the correct constant. Okay, so now let's go with the next problem, and we'll start with the same procedure. We do the ice table. Initial, we have the solid. The changes is going to be x. At the equilibrium, we're still going to have the solid. We start with 0 plus x is being generated of lead 2 plus, and 2x is being generated of the iodate ion. So at the equilibrium, we have x and 2x. Our solubility product constant, it is going to be the concentration of lead 2 plus times the concentration of the iodate ion squared, which in terms of x is going to be x times 2x squared. This is going to give us 4x cubed. And the constant that we're given in the problem is 3.7 times 10 to the minus 13. Okay. We know that this is equal to 4x cubed. Thus, x, it is going to be 3.7 times 10 to the minus 13 divided by 4, elevated to the 1/3. So our value for x becomes 4.52 times 10 to the minus 5 molar. Now, to get the concentrations of Pb2 plus, this is going to be the same value as x, and in the case for the iodate ion, this is going to be 2 times that value. So 9.04 times 10 to the minus 5, and molar in both scenarios. You can also use these concentrations in order to verify that your result is correct. If you take, for example, the square root of that final concentration and you multiply it by the other value that we have, you should have the same value as KSP. So this is the final solution. These are the concentrations for both of the problems, and that would be all.